You hear the term artificial intelligence all the time, right? We think of machines that can learn, that can think, but what's really going on under the hood? Today, we're diving into the ideas from the book Why Machines Learn to get at the beautiful, elegant math that's really the engine behind modern AI. Let's do it. And hey, it's not just me saying this stuff is a big deal. Geoffrey Hinton, one of the absolute godfathers of deep learning, called this book a masterpiece. Why? Because it connects the pure math to the human story behind it. When a guy like that says something, you know you're in the right place. So, this all boils down to one huge question. Let's cut through all the hype. How do machines actually learn? And how on earth does something as abstract as math power all this world-changing tech? Well, that's exactly what we're about to find out. Okay, if you strip everything else away, machine learning is really about just one thing: finding patterns in data. That's it. That's the whole game. The book describes it as a desperate search for patterns. And honestly, that's the perfect way to put it. It's the foundation for everything that follows. All right, have a look at this simple table. You've got 3 columns: x1, x2, and y. I'll tell you right now, there's a very simple hidden rule that connects them in every single row. Go ahead, take a second. See if you can spot the pattern that gets you from the first 2 numbers to the third one. Did you get it? The hidden rule is a simple little equation. Y is just x1 plus 2 times x2. Now, when we say a machine learns from this data, it's not magic. It's just doing the math to figure out those key numbers, the 1 and the 2. We call them weights. In other words, it learned the rule just by looking at the examples. And what you've just seen is a perfect little example of a core idea in machine learning called regression. The easiest way to think about this is predicting house prices. Your x1 could be the number of bedrooms, and x2 could be the square footage. A machine can look at thousands of house listings, learn the weights for those features, and then build a model to predict the price, y, for a brand new house it's never seen before. Okay, so predicting a number like a price is one thing. But what if the goal isn't a number, but a decision, like a simple yes or no? Well, this is where we shift from prediction to something called classification, which is really just the art of drawing lines. So, with classification, the output is a category, not a number. For instance, is a patient high risk, we'll just call that 1, or are they low risk, which we'll call -1? The machine's job is to look at a chart of all the patients and find a single line that perfectly separates the high-risk group from the low-risk group. Now, if you have more than 2 features, that line becomes a hyperplane, but don't worry about the jargon. Just think of it as a dividing wall or a boundary. Now, that sounds easy enough if the data is clean. But what happens when it's messy? When your high-risk and low-risk patients are all mixed up on the chart and there's just no way to draw one single straight line to divide them? This was a massive roadblock for early AI researchers. It seemed like an impossible problem. The solution to this is, no joke, one of the most elegant and just plain cool ideas in all of machine learning. It's called the Great Kernel Trick, and it's a way to solve an impossible problem by kind of bending the rules of space itself. This visualizes it perfectly. So in step 1, you see the problem. The red and blue dots are all jumbled up. You can't draw a line. But then, in step 2, a special math function basically launches all of that data into a higher third dimension. And poof! Look at step 3. Up in this new space, the 2 groups are suddenly easy to separate. You could slide a simple, flat sheet right between them. The impossible problem just became simple. But here's the truly brilliant part: the trick in the kernel trick. This method, which was developed by pioneers like Vladimir Vapnik, Barnhard Boser, and Isabelle Gaillon, means the algorithm never actually has to do all the super complicated math in that higher dimension. A clever function, the kernel, lets it find that separating plane while all the number crunching stays in the simple original space. It's an incredible mathematical shortcut. All right, so finding patterns and drawing lines is one thing. But how in the world do machines learn to do something so incredibly complex, something we do without thinking, like seeing? Well, the inspiration for the answer, believe it or not, came from a Nobel Prize-winning experiment that involved a cat. So, 2 neuroscientists, Hubel and Wiesel, made this amazing discovery about how vision works. They found that the brain's visual cortex is built like a hierarchy. At the bottom layer, you've got simple cells that only fire for really basic things, like a vertical line or a horizontal edge. Then, the next layer up has complex cells,
that take the signals from those simple cells and combine them to recognize more complex shapes. It's like building with Legos. You start with the simplest bricks and build up from there. And that biological discovery directly inspired the design of something called a convolutional neural network, or CNN for short. A CNN is literally built to mimic that brain hierarchy. It uses layers of digital filters. The first layer learns to spot simple patterns, like edges. Then the outputs from that layer get fed to the next layer, which learns to recognize more complex stuff like an eye, or a nose, or a car's tire. So how does this work in practice? Well, a computer doesn't see a picture of a cat. It sees a giant grid of numbers. That's it. Each number just represents the brightness of a single pixel. This huge spreadsheet of numbers is the raw data, the input that starts the whole process. Then a little grid of numbers, this is our filter or kernel, slides across the entire image. You can think of this filter as being like one of those simple cells from the cat's brain. It's trained to look for one very specific tiny pattern, like a vertical edge. The network will have thousands of these different filters, each one hunting for its own unique little pattern, building up a complete understanding of the image layer by layer. And this right here, this is the fundamental shift, the whole game changer. In traditional programming, we give the computer the data, and we write out the exact rules, and it gives us the answers. But with machine learning, we flip that completely on its head. We give the computer the data, and we give it the answers. Like, here are 1 million pictures that are already labeled cat. And the computer figures out the rules all by itself. Now, this new way of doing things is what led to the massive AI models we have today. They are incredibly powerful, but they're also, well, they're a little bit mysterious. It's time to try and peek inside what everyone calls the black box. So, take a look at this. Google's Minerva model got this algebra problem. Now, what's incredible isn't just that it got the right answer, which is -10. It's that it showed its work. I mean, look at that. It lays out a step-by-step process that looks perfectly logical. It really feels like it's reasoning its way to the solution. And this leaves us with the biggest, most profound question at the very heart of AI today. When a model does this, is it truly understanding what concepts like slope and coordinates even are? Or is it just executing the most complex, most elegant, and most powerful form of pattern matching that humanity has ever created? Right now, the top minds in this field are fiercely debating this, and the honest truth is, we don't have a clear answer.